Yeah, thank you for the introduction. Yeah, my name is Wei-Chih. I'm from the Preon team. So actually, our team is a combination of people from the industry and the academic people, and we have a lot of experts from about it. They are experts in the theory of the so-called ZK snark. So yeah, I might not be the best person to present here, but I try my best to so yeah. So let's start. So sorry. So the first question is why Preon? So as far as I know, Preon is a very small particle. So so why is the name Preon? So it's something that it sounds like that we intend to design a system that produces the smallest signature size post-quantum cryptography schemes. But it turns out that we are on the left top, so we have the gigantic signature size. So so this seems to be a very good example of bad communication between the marketing team and the engineering team. Yeah. So, but actually, why we are designing Preon is to design a signature that's beyond current digital signature. So, so this might be a little bit off topic to this Anis call for the standard digital signature, but so this standard digital signature on a message X is that usually says that I swear that the signer sent the message X, but what we're trying to design for this so-called beyond digital signature is that we try to provide a scheme that can prove that the signer says X, which I'm not going to disclose here, but I swear that this X, if you plug it into a function f, it produces y. So so this turns out to be very functional. I mean, it can be applied in many advanced scenarios. For example, in this digital ID scheme, we can prove that I am a citizen and I'm more than 18 years old, but I don't reveal any confidential information that I would not want to reveal to you. But still, I can sign a signature or a proof that can prove to you that I'm over 18 years old and I'm allowed to buy alcohol here in UK. So yeah, so so we would like to say again that we intended to go a step further from the current signature schemes. So so the overview of our Preon signature scheme is pretty much very similar to the MPC in the head, especially the fees that Lawrence just introduced. Yeah. So, but Lawrence also mentioned that there's another group of zero knowledge proof systems which produce so-called succinct proof. That's called ZK snark, and that's what we are using here for constructing Preon. And the one-way function that we choose is the same. It's the AES. Okay. So I will talk more about this ZK snark later in the later slides. So yeah, that's the whole picture of this Preon signature. So yeah, so Preon in Preon we instantiated this ZK snark using this scheme called Aurora, which is a post-quantum ZK snark, which I will introduce a little bit later. And the way we use AES as the one-way function is quite similar to Feast, but instead of using only the ciphertext as the public key, we use both the plaintext and the ciphertext as the public key. And the secret key for this encryption is the private key. Okay, so we share the same benefits of using this kind of construction, that we have both small private key and public key, which are just keys and plaintext, ciphertext of AES. And but people who are familiar with this ZK snark will know that, and also shown in the first slides, that the main drawback of using this ZK snark is it's extremely slow, and the proof it generates is quite large. It's asymptotically succinct, which means that the proof size is in something like a log or a log polynomial, but which MPC in the head grows linear. But in the sense of this general purpose signature, yeah, the schemes using MPC in the head can fully optimize for this specific. But what we are trying to do is to be able to prove a more general problem, not only limited to this AES. So it will, yeah, generate large proofs, and so the large signatures. But what we have done is combine these two, but we add some optimization here. So we replace the prime field that used in the Aurora proving system with binary field, so that it's more compatible with the AES. This will be introduced later. And so this could greatly reduce the number of constraints in describing this AES. And we can use a faster arithmetic. It's called additive FFT to speed up the proof generation, the signing process, and also smaller signature sizes. So this is just a brief description of what ZK snark is. It stands for zero knowledge succinct non-interactive argument of knowledge. So yeah, basically just the prover can prove that some secret witness, W or omega here, satisfies this function here. So, and the succinct means that the proof size is relatively asymptotically small. Usually it's in log polynomial. Yeah. So next I will briefly talk about the Aurora proving system that I'm using here. So so in this type of system, we first we have to encode the system that we are about to prove using a representation called R1CS. This is just the AZ times BZ equals CZ here. So the ABC here are huge matrices depending on F, which we call the constraints of these variables. And the Z here is a vector that includes public, constant here and public information. And this W is the secret witness information that we want to reveal. So So this turns out this R1CS representation is very versatile. It can represent a wide range of circuits, so-called circuits. That so in order to prove this relation, and we have to do this kind of checks. And so first we have to do this polynomial interpolation to encode this this R1CS into polynomials, and we have to do this lin check and row check. So the lin check means that we use some IOP called Reed-Solomon encoding IOP to prove that there is a vector A that equals A times Z, B equals B times Z, and C. And then we use the row check to prove that these two A times B equals C. So this circle times here means it's element-wise multiplication, not inner product, also not matrix multiplication. It's just element-wise multiplication. And in this Reed-Solomon encoded IOP, what we need to prove next is that this encoded polynomial has a low relative, so its degree, this encoded polynomial has a lower degree than a certain bound. So we invoke this so-called FRI protocol to test, to commit and test the polynomials in this lin check and row check actually has the low degree that we intended to have to the verifier. And so far these are all so-called interactive Oracle proof. So it's actually back and forth, some commitment and queries back and forth between the prover and the verifier. So next we have to use. So when we are generating non-interactive proof, we use this so-called BCS transform, which is actually just Merkle commitment, just like many MPC in the head schemes use, and also use via Shamir to turn it into a non-interactive protocol. Okay. So I have mentioned about this Reed-Solomon encoded IOP. So the basic idea of this basic process or the idea is that when we try to prove I know that some vector Z in this vector space V, first I use this Lagrange interpolation to we first view this vector as a function. So from this H to FQ, and then we use Lagrange interpolation to interpolate a polynomial, which is the R here. And so this is a degree less than this H polynomial. And then we have to mask this polynomial with some random function multiplied by this vanishing polynomial. So it turns out that we have this fz of x has the same value, evaluation value on every point in this group. So so the verifier can now query some x's some values in another set of values, which is L, and the zero knowledge part of zero knowledge property comes from the fact that this H and L are actually disjunct. They have no intersection. So that even the verifier queries number of evaluation values on this L doesn't leak any information to the verifiers. He has no idea about what this R is. So yeah, and then we have to check this polynomial fz is the degree of this fz is small enough. So it is not a randomly high order polynomial that in this. So here is an example in our Preon 128 scheme. The size of this H is about 2 to the 12, and the size of L is 2 to the 19, and the FI test for the degree is lower than this 2 to the 14. Yeah, so I guess I just don't go into too much detail, but the Aurora proving system is pretty much, the flow is like this. So we have to compute this interpolation of this polynomial, use Lagrange interpolation to produce this polynomials, and we have to encode them in using Solomon code and commit to the verifier, and the verifier samples this using random oracle. This challenges here, and then the prover have to compute this subsequent formula values to reply to this verifier. So there's another trick here is that in this lin check and sum check. Lin check and row check. Actually, we have a bunch of polynomials that we have to run through this FRI. But in order to make it more efficient, we actually only test on a single random linear combination of this bunch of polynomials, so that we can make it more efficient here. So this is the ugly formula here. So yeah. So next, I would like to talk a bit about the R1CS. So turns out the formula, the form here, this AZ times BZ equals CZ, is very useful when you can use it to express many, for example, these high degree polynomials, and also you can do range check, yeah, and also you can do something like program here. You can check if B the value of B is 1, then R equals to T. If it's 0, then yeah, it's equals to F. You can do checks like this. So it's very useful and very expressive. You can use it to express many. But there's a problem in using prime field for expressing this crypto schemes like AES. So what we just like I mentioned, we replace, not replace, we use the binary field instead of the prime field in this Aurora system, so that we can come up with a very efficient expression, R1CS constraints for the AES schemes. For example, just maybe just like Feast, Lawrence has mentioned, this inversion in this S box is very easy to express in using only one constraint. With, of course, you have to add several range checks for this because these are binary values. So we have to check there are only 0 and 1 values for Y and H, but you can use and also for the problem that when this B is equals 0, there's no inverse. We can actually encode it also encode it in using R1CS and combine them into one single constraint. Yeah. So I did not write down the constraint here, but you can take a look at our submitted paper. You can check out there how we combine this. So it turns out that by doing this, we are able to reduce the total amount of total number of constraints for example, for AES 128 from this 14,000 to only 3,600. So this greatly reduced the sizes of this matrices in R1CS and also the signature size. But of course, our signature is still too large. But yeah, this is we have done some work on this. Yeah, we try our best so far. Yeah. So about the parameter selection, we actually provided 3 sets of parameters, namely the aggressive, balanced, and conservative. The conservative comes from the original Aurora paper. There, the parameters there is very conservative, and the signature size is, and the verification. I mean, the proving time is too large. So we would not suggest this conservative parameter set. Only the aggressive and the balanced parameter sets are recommended too. So the difference between this aggressive and balanced is that the aggressive parameter set, we assume that assume an attack on the FRI IOP is the best attack. We know that so it's something like you just guess, because this we use Reed-Solomon code here with code rate row. So if an attacker want to cheat or want to make he can just guess something like a brute force or maybe a guess. So one in maybe he has the success probability of row to cheat that he knows the low degree polynomial, but because we are we will repeat the process L times, so the success probability of cheating is row to the L. So so based on that, we can, if we, it's the best known attack so far. So I think if there's no new attack, then we are sure that this aggressive parameter set is it's safe here. So so the performance here is not, I think it's not the best result that we want to see. But so first of all, the signature size is too large. But we and also the timing here so the research field of zk-SNARK is a very fast evolving area, so to speak. So I think we are still working on new improvements, and all the researchers in this field are also working on new optimizations. So so far, and also our implementation is not quite optimized here. So you can see that the signing time or the proof generation time is not what we expected. But so this is the current status, and so we hope that we using this zk-SNARK and this R1CS can introduce more functionalities in our signature schemes. So
And our preliminary security analysis based on previous work and our own analysis, we provide this aggressive and balanced parameters that can meet this requirement, security requirement. And of course, we have small key sizes, but rather big signatures, which we will improve. And also, the current implementation is rather slow. But just like I said, it's a rapidly evolving field for zk-SNARK, and we are diligently working on the improvement. So maybe I just talk a bit about this. We are working on this so-called Preon Plus. So we will use, in which we will use this Cantor basis and additive FFT to speed up the signing procedure. And also, we are working on this more efficient R1CS encoding to reduce the signature sizes. So in some preliminary results, we already have an optimized implementation that can finish the signing procedure in less than 1 second. That's a great improvement of this Preon, but still a lot of way to go. But yes, I guess I just conclude my